Yeah, good evening to all. We'll start in 1 minute, okay? Share my screen. Yeah, we will start the session then. Okay. I think some members are new here, so I will introduce myself again. So I'm Swapnil Mane. I'm doing a PhD at IIT Jodhpur CSE department. Currently, I'm working in the domain of social network analysis and natural language processing. These are my main research area. Yeah. Yeah, I think let's jump to the questions. So here we primarily discuss the questions of the last year's assignment uh, of the respective week wise. So this is an week six assignment, last year's questions. So from this question answering live interactive session, you will clear some doubts, or you will recall some concepts what has been covered in this week, or we'll discuss if you have any queries regarding any concept, you're not understood anything. In that case, you can ping me, we will discussion on that part, or that concept, okay? So the primary aim of this session actually is that after means while um, taking these questions, I will explaining the concepts of that particular question. So that will be helpful to solve your this year assignment questions, okay? Yeah, let's start from the first question. So the question is that what happens when the gold coins distribution game converge? So what do you think that? So firstly, what is an gold distribution game that we have seen in this week lecture? What is an gold coin distribution game? Anyone can explain? So in gold distribution coin, there was we have discussed the two methods: equally distribution method, and another is an random walk method, right? In the equally distribution method, in that we have discussed that. So whenever we have discussed any neighboring node, so we have means suppose let's take an one sample network. So here is an a network. I have taken one example, right? It's not an. So this is an A, B, C, D, E, right? Suppose I'm at a location. So currently at this position, and this node has an suppose 10 coins. So in the gold distribution game, there is an in the equally distribution game, in that method, what we are doing, so a has an two neighboring nodes, actually two edges are there, so we have equally distributed these 10 coins among their neighbor nodes, actually B and C, right? So So B will get an 5 coins and C will get as an 5 points, right? So this way, this game is implementing actually, right? So here, suppose, and this is in first iteration. After the first iteration, B got certain 5, C got certain 5 from A, right? So B, suppose B has an at the initial stage, B has some coins, right? Suppose it has an 12 coins. So in that case, it has been divided among the C, E, and D, right? Equally 12 divided by 3, likewise, and C will get as in 3 or 4, right? 4, 4, 4. Right, likewise. So after the first iteration, first means while doing this, this is an first iteration process I'm discussing here actually. So here it's not like that 5 is divided among the three neighbors. Right? The 10 is divided among the three neighbors. So the first, let's see. So I think you recall this the process of the gold coin distribution, equality distribution method, right? So after recalling this, what do you think that which option is correct? So for first option is that all the nodes get equal number of coins. That is true, but this is one way of process actually. It's not after the the question is asking about after the converse means when the game is converged. At that time, what is the position? What is the condition of the network, right? And what we'll get from the network that we have. So this is the process actually. This all nodes get equal number of coins, right? This is one process. So another is that all the nodes are visited. So in the equal distribution, all nodes will get as in visited actually. There is some issues while implementing this algorithm as well. That is an sync node will be encountered. So that is an telecorporation we are calling that, right? So we are randomly selecting any node from the network, and then we are uh, starting the things, means that will be implemented in the random walk actually. But in equally method, there is an also suppose there is directed graph, and in that directed graph, so one edge will be gone to the one node actually. So there is a no as such subgraphs are there, means sub trees are there. In that case, the process will get stopped there, right? But in the equality distribution method, it is surely all the nodes will be visited, right? It is an means the algorithm is designed like this way. It will get as in all the nodes will be visited actually. How will visit it? So let's suppose we have an suppose an A has an B and C neighboring nodes. So from an B and C, we are randomly selecting neighbors from the B and C. So let's suppose the algorithm has selected an B. One second, right? So at that time, the age weights is equally distributed among the B and C, right? After suppose after visiting the A, I have visited the algorithm has visited to B. So in that case, B has a neighboring nodes. Let's take a C, E. E is already visited, right? C, E, and D. So among these nodes, it will be randomly selected again. It right. Likewise, the algorithm goes. Okay. Yeah. So what do you think? Which option is correct here? Is anyone? So let's see the second option. All the nodes are
Correct.
visited.
Third option is correct.
So Jancy, why is that? Why the third option is correct? Yeah, so this goal distribution game we have primarily used for the page rank algorithm, right? Page rank means we wanted to find from the network, we wanted to found that which node has an popular or which node has an important, right? So for that we require a ranking of the nodes, and we are doing the ranking based on his score, page rank score, right? So this is an gold distribution game. So in that context, you can consider which node has an highest number of coins, that node as an popular or important, we can say that. Okay, in this, in the context of this game, actually, gold coin distribution. So after convergence means each node has get different number of coins, right? So based on this different number of coins, we are assigning the ranks of each node, right? So suppose it is an after iteration, so we got as an same number of coins to all nodes. So that is a not converged point, actually. We want a converged point, and when we will get to know that at which point the network is, or the game is converged. How we will get to know that, right? There is, and suppose in each iteration, in the further iteration, we are getting the same weights. Same weights means, for means what? Suppose iteration is equal to 10, we are getting as an a is equal to iteration 10, a weights got as an 10, and iteration 11 also we got as an a is equal to 10. Iteration 12 also we got as an a is equal to 10. So at that point means some decimal points differences are there, but at some point of time, will very high iteration you are doing at, means high number of iterations, if you are doing at that time, you will get as an converged state of the network. So at that converged state, all the nodes comparatively is a different coins, we will get it, right? So the option 3 is correct right here. The one node gets all the coins. It's not like that. Okay. So one gets all the coins means the network is like that, right? And in that also, means this is also not possible. In this network also, it's not possible, because you can see if the this node is visited, then it will be distributed among his neighbors. Actually, you can see here among his neighbors. So in this network also, it's not possible to get all the coins at a single node. Okay. Uh, yeah, I hope this question or this concept might be your cover, means you cleared it. Okay. If you have any doubts, let me know in that case. Okay. Let's jump to the question 2. So this is also game distribution problem. In a game distributing gold coins across a network, each node begins with an equal number of coins, right? So I had already, as mentioned in the week lectures, that initial point we can take as a different coins as well, but uh, in lecture also they have taken as a similar number of weights. We are in the further questions, we will discuss questions also. At that question, the initial point of time, each node has a different weights, and considering that, we had to calculate how game distribution or equal distribution method will be implemented, and how the weights are updated. Okay, let's see that question after the further uh, slides. Okay. So at initial point of time, the each node begins with the equal number of coins, right? Then following one round of redistribution, the total number of coins across the network remains the same. So considering this situation, which network structure guarantees this outcome, right? Means which network has guarantees that after one iteration of the equal distribution of the coin, every node gets an similar same number of coins. Yes, anyone? So which the first random network, it's not defined actually. Every time you will get as a different uh, network actually, right? So it depends on the probability of age you are giving in the, means you are passing the p is equal to which value, depends on that you will get as an different size of the network. Means the number of nodes are same, but the ages are differ based on the probability p is equal to. Then scale-free network defines that as an, it's not covered at this point of time, but it assume that the scale-free network is a real-world network. Real-world scale-free network means what? So, uh, so there is an, let's take one graph here, means plot, and in the network there is an uh, low number of, means what we can say, it's like that. So number of nodes, these are the number of nodes, and these are the degree. So low number of degree users has an highest number of, means number of nodes who has an low number of degree, those nodes has an very high. Comparatively, those nodes who has less degree. So I think I have mismatched, means, one second. So this is an, so those users has a low degree. The number of users of that low degree users is very high. Comparatively, some users are, some nodes are there which has an low, which has an higher degree, but number of nodes is very low. Let's take an one example, that is, an in Twitter we know that there is a lot of users who has low number of followers count, right? Means it's common users, or those users has a low number of follower count, but there isn't some influencer accounts are there, right? In that influencer account, those accounts has an higher number of followers. So you can observe this, in comparatively the followers accounts, in comparative the common accounts, it's very less, right? There is a only less number of nodes are there, less number of accounts are there who has a higher number of followers, and there is huge number of accounts are there who has lower number of followers. So the followers consider as a degree. Okay, so this represents a network actually, right? So here the node is represents an user, and the connection between the user is and followers. So which user has an higher degree means his connections, right? And he has a higher degree means he is an influencer node, but he has a lower degree means he is a common user, right? We have as an 100 or 200, 500 followers are there, right? So, so likewise, after drawing this network number of nodes and degree plot, it will look like this way. This is also this way. It depends on where you are putting the degree and nodes. Based on that, this plot is look like. Okay. Yeah, let's move to our problem actually. So I have explained the what is an scale free. It's look like, which is, and simply don't get confused about it. So it assume that this is an real world network. Real world network, that is an already in the lecture has taken as an one real world data set, that is an citation network. Though there is an research papers are there, the node is an research paper, and the link between the research papers as a citation. So this paper referred to this paper in his paper, right? Likewise, the edges are drawn the network. So each node represents a paper, and the edge represents as a citation. This paper has cited this another paper. Likewise, the network is. So this is also scale-free network, which is a real-world network. It's not random network, right? Random network might get as an equal degree, right? That is a state degree. Every node has an state equal degree, might be. Ring network, in the ring network there is an only two edges are possible. Let's assume that a ring is a simple ring. What How the ring structure is represented? Likewise, this is one type of ring. So this is a ring network. So I have explained the what is a random network, scale-free network, which is a real-world network, and another is a ring network. So, considering these networks, what do you think that which uh, option guarantees this outcome? That is, every nodes get as an equal number of coins. What do you think that? Yes, anyone? Okay, see here. So the let's take an this ring network. So here is and is equal to 10. It is distributed in 5. Suppose he is as also, they have mentioned that it begins with the equal number of coins. So every node has an 10 coins. Suppose let's take as an 10. Okay. So you can see after the first iteration, every node gets a 5 means while I have visited the A, his neighbors gets as in 5 and 5, right? You can see here, and after visited to the another node, so the A also get as in 5, and his neighbor is also get 5. Likewise, you can visit this, he will get 5, he will get 5. This he will get 5, he will get 5. Likewise, if I visited this, if he will get 5, he will get, sorry, he will get 5. Right. One round of, so you can see after the one round of the redistribution, the total number of coins across the network remains the same, right? So the correct option here is the third option. Is there any doubts, or you are not understood anything? I will explain it again. Okay, that case. Yes, anyone? Okay, let's move to the another question. Which of the following statement is true for teleportation? It already explained in the first question while discussing about the uh, coin distribution or distribution equal distribution method. Right? So, can you explain what is in teleportation and where this problem we have incident? In which method we have seen two methods, which is an equally distribution method, right? Another one is an random walk distribution method, right? In the random walk we are giving the all the coins to visited node. Likewise, yes, Jansi, yeah. If it is wrong answer, it's fine. Okay, it's not. Yes. What is in teleportation? Firstly, so we have seen this concept in the random walk method, right? In the random walk, we are means we are visited node randomly, right? Means suppose we have considered, let's take an node, right? Suppose it's take as initially selected a random node, right? From that random node, it is visited to this node, right? Then in this node, likewise, any node, but take as a neighboring nodes, right? This node, and it's not this node. If this point at time it is in sync, means it's already visited, it gets cycle. Then another is this node, right? At this point, it gets stuck. You can see here at this point of time it get stuck. There is no further exploration of the network, right? Suppose I have started the I have started from this node. So let's take another color. Started from this node, then I have visited this node, and then I have visited this node. Visited means this node, this node giving his all the coins to his this another preceding subsequent node, right? Then after this, if he is visited to this node, this coin, then his all the coins is given to the this node, right? Means this last node. So you can see here there is no further exploration. The network or random walk gets stuck here. Right? This is an sync node. Right? There is no further exploration of the network. So this problem we have incidented in uh, random walk problem, random walk method. So at that time, what we are doing? So the suppose I have explained the solution of this, then already the answer I will give it. So what do you think that? So this is an teleportation actually. This problem states as an teleportation, right? And that node represents sync node. So considering this, I have explained the teleportation example here or concept here. So considering this, what do you think that which statement is correct related to the teleportation? Yes. Prevents random walk from getting stuck in certain regions of the graph or jumping to any random. So this is a one problem. Teleportation is a solution for this problem. So for getting after incidentating this problem, which solution we can incorporate? That solution has stated in the statement 1 and statement 2, right? The first solution is that prevents the random walk from the getting stuck in certain regions, means that is one thing. And statement 2, jumping to any random node in the, I already explained the some answers here while I'm explaining this concept. So anyone wants to guess the answer, which could be the statement is correct related to teleportation? See, we have we have seen the problem. Where is the problem actually? That we are inserting the sync node, and we have to resolve this problem or address this problem by using a teleportation method. So a teleportation method, that first statement is already I have explained, that is, and prevents the random walk from getting stuck in a certain region of the graph. Means this is a region that the random walk has stuck here. So teleportation is an one solution for that. Okay, so how it is implement working? So how it is working, that is statement 2 is stated, that is, and it is jumping to any random node in the network. So if I get stuck here, then I have jumped to any random node. So I will jump here, right? Then the random walk start from this node. It will be visited this, then visited this, then visited this, they visited this, visited, then again stuck, then I will again it will jumps to the another location likewise. Okay, so number of iteration that depends on us, right? That we have seen in the implementation part of the lectures, right? So here you can see the both option is correct. I hope you have understood this question. Let's move to the,
Yes, sir.
yeah. Let's move to the another question. If NX represents network library, NX, that we are using a shortcut key, that means every time we don't require to write whole the network X, right? So how we are writing it, I will record here. So the import net NX. Sorry, it's not maybe. My handwriting is very bad. My iPad. Network X as NX. So it is a shortcut. It's not like as an NX is an library. Okay, that means there. Might be you have seen in the coding part of the lectures. Okay, if NX represents network X library, then For a graph G, what does nx dot page rank G returns? So this has already implemented in the lecture. I think, I hope you have also implemented uh, in your desktop, right? In the page rank represents, it gives values actually for a node, right? So for which reason we are using the page rank? We are finding from the network, we are finding popular node or important node from the network, right? By using some weights, right? So means what we are doing, for each node we are getting one values actually, and that value at this point of time you can consider that is an important score, right? How much that node is important, it is giving as one score. Which node has an highest score, those nodes has, that node is an important node, and based on that scores, important scores, we are ranking the nodes. The highest score node gets an one rank. After that, which one is an second highest, which gets as a two rank. Likewise, we are giving the rank. Based on the rank, we are giving those results to the users. So in the context of the searching problem, that is, and I'm searching one web page, that already explained in the week lectures as well, but I will also recall here, or also explain it again, which is, and suppose you are searching any page or any web page, any result of your query, and you want a web page which is an well suited for your query. So there are huge number of web pages are there, right? So behind of the Google console, what it happens, based on your keywords, they are shortlisted the web pages. Those are shortlisted web pages are more than the 10 millions, or it's maybe it's not uh, defined the count actually, right? It is an 10,000. Let's take as a simple 5,000 count, right? From that 5,000 we want mostly relevant web page to your query. So for that, what we are doing, we are applying the page rank. That is, an Larry Page has designed that algorithm, page rank algorithm, which gives as an each web page has a score based on your query, right? And then after giving the assigning the score for each web page here, let's imagine that each web page is in one node, and link edge between the web pages, which is an in between the node, which is an hyperlink. It is an refer to this node, this web page refer to another web page. Likewise, imagine this network, and based using this network, the page rank algorithm is implemented over this network. Right, I'm giving only a simple intuition about this page rank. Right. So after applying the page rank on that network, you will get each web page as an one important score related corresponding to your query. Important score, and based on this important score, it ranks the web page. And based on this ranking, you will get a 10 top web pages on your first homepage console. Means while you are writing, and after the to search bar, you will get an 10 pages, right? Almost 10 pages, which is an highly ranked to your query. So for this application, there are many applications are possible by using this page rank. So you can find important friend or popular friend in your network as well, right? And highly cited or highly important paper in the citation network as well. Okay. So likewise, there are multiple applications are there. So, so what do you think that? So I have explained the overall idea of the page rank. So what we can expect, page rank will returns actually. Right? There are, you can see these are the options are there. The list of nodes, what it can returns, the list of nodes in the ascending order of their page rank. Means what it is saying, ascending order means node, you will get the list of nodes, and it is an sorted nodes based on the page rank score. So each node has a page rank score. Based on that page rank score, it is an already sorted list of nodes you will get from the page rank, this uh, means this library or this function. So is it true? It is will get an ascending order uh, number of node means no list of nodes. The second option is that a list of page ranks of all nodes. So it is saying that we will get only single list. In that single list, the each item of the list it represents as an only the score of the node. It is not as in which node. We don't have that information. Only we have a score of the node, and which score represents which uh, assigns to which node, that information has not is captured in that list. Actually, we can treat as an index one page rank one, but it's not like that. Page rank returns that value, this list. Another option, which is an dictionary of node and page rank pairs. Dictionary of node page rank pairs. The dictionary has a key and values, right? As you might know already, key and values are stored in the dictionary. That is a traditional method. That is a traditional. This is a method of the dictionary. This is how we are storing the dictionary. That key represents the node here. They are saying that in the third option, and the value represents the page rank value of that particular node. A node and his value, his page rank score, comma another node and his page rank value. Likewise, the dictionary it can read us. So this is an three options means that I have explaining how this representation look likes. And another option is a dictionary of age page rank pairs. So this represents how this is represents the key represents here as an age. Age means suppose A to B. This is a key, right? And his value is an page rank value. So its page rank value represents an age. So what do you think? Which option is correct? Which option is well suited for this page rank that I have already explained how the page rank works and what it returns, what can be it returns. If it is correct, incorrect answer, it's fine. Let's discuss it. It is an interactive session. Okay, it's not I'm talking one side alone. Okay, you can also discuss or point out anything you if you want. What do you think? Which option is correct here? Anyone? So here already explained. We want means page rank returns uh, node means it returns a page rank score of node, not as an age. So this option is already on, means, right? It's not about the ages, it's about the nodes. So it's not true, right? This option is not true. Firstly, it's not doing a sorting itself. We have to do sorting after getting the output from the page rank, right? So it's not like that. It gives an sorted list. The second option is that list of page rank of all means it is giving only the page rank value. It's not also possible. Means it's not possible, but it not returns like this way. Right. And second option is correct. Actually, it returns a dictionary, and from this in that dictionary, the node is an key and page rank values and the value of that particular node. So this is how the page rank returns. So this is also implemented while the coding part of the lectures, right? After getting the values from the page rank algorithm, that ascending sorting we have done right in the lectures. Might be you have seen, you will recall it. Yeah, yeah. This is very simple. It's not that much difficult to understand. Can also implement.
Sir,
See, yeah,
sir,
Jansi.
one second. Fourth question, sir.
Yes, go ahead, Jansi. You're not audible. Hello, Jansi, you're not audible.
Yes, sir, I audible, sir.
Yeah, you have any questions or any query about the question 4? Okay, if not, let's move to the another question. Yeah, here we have to solve this question actually. This is an how that equally distributed gold coins, that method we have discussed, right? Two methods we have discussed. The first is an equal distribution method, another one is an random walk method. In the random walk, we are what we are doing, if we are visited a subsequent node, whatever nodes, whatever coins I have already, I will give to that particular node, all the coins, right? Likewise, the algorithm works. Okay, if it is uh, visited another subsequent node, it will give the all his coins to the his subsequent node. It is a neighboring node as well. Okay, and equal distribution node, in that what it is happen, suppose I have the node has an two connections. At that time, whatever he has coins, it is distributed equally. Suppose it has an 100 coins, then what that node it can do, it will distribute 50 coins to the a the his first neighbor, and 50 coins to the b neighbors. Like if it is has an four neighbors, in that case four equally distributed, 25, 25, 25. Likewise this. Let's see, after solving this question, you will get you will you will you can clear the doubts, or you will in detail clear the process of the equal distribution method. Let's try by yourself firstly, then I will solve it again. Okay, no problem. Take a time, read the question carefully, and consider this network. And considering this network, try to solve this page rank algorithm. You can use any method, that is an random walk. Best suitable method is an equal distribution method, right? By manually method. Okay, so if you want to do random walk, you can do it, but it's suggested which is unequally distributed, right? I already explained how the equal distribution works. So there are the question says that at initial point of time, each node has an 1 by 4 a weight. A weight we can say that that is in points. We can say that that is a score 1 by 4. Each node has an at initial point of time, and we want to find that after the two iteration of the page rank, after the two iteration, what will be the score of each node, page rank score of each node. Try yourself and let me know what could be the answer. If it is wrong, it is fine. Okay, but try to dig into the problem and try to explore the problem. Okay, anyone has got the answer? Take a time, no problem. Yes, anyone has got the answer? Or anyone has tried or not tried? Means if you are in intermediate state of the problem, let me know which problem you are facing. Okay, it's fine. Yeah, let's start. I will try to solve this problem, or try to know I will solve this problem. Okay. Yeah. So the question has already mentioned that each node has an initial point, initial score is an 1 by 4. Right. Let's take as an 1 by 4, 1 by 4, 1 by 4, 1 by 4. I think, I hope it is an visible. I will make it more. Okay. So let's start from the A. Okay. Let's start from the A. First I visited. You can visit a random node, right? But for the simplicity, for the means for the chronology, let's take as an A. We can take as an any node. So firstly, we have taken the A, and A has an two neighbors, two directed means out degree nodes. If it is in degree, we are not considered. Means you can see here in degrees, incoming node, incoming edge is also there, but we are not distributing the weights of the A among the D as well. We are only distributing the weights between the B and C nodes. Okay. So here, after considering the B and C outgoing nodes, what could be the distributed weights? So let's take uh, 1 divided by 4 divided by 2, which is an what could be the 1.25, right? So after the first, while the first iteration, A got as an 0.125. Also C got as an at first iteration, right? This we are uh, taking means we are keeping the log of that particular values, how we take, how it is getting 0.125, because we have distributed equally among these nodes B and C. If it is wrong, I'm going any wrong calculation, please let me know in that case. Okay. Let's after that, let's algorithm has, or we will visit option B, means node B. Okay, node B has an weight 1 divided by 4, and he has an on outgoing edge only 1. So 1 divided by 4 divided by 1, which is an 1 divided by 4. So at the first iteration in the log, D gets as an 1 divided by 4, 1 by 4, right? Because it B has an only one single edge. We are not considering these updated weights here. Okay, means these weights we are not considering. Okay, only the initial weights we are considering while the first iteration, means before the first iteration gets the results. Okay, right. 1 divided by 4, like, so we have visited up to now A visit, no, node A visited, B visited. Let's visit the C. So what the we have visited C. So the C has an 1 divided sorry, 1 divided by 4 weight. So it has an outgoing edge as an B only, right? So that is also get as an at the 1, means at 1 I'm writing here because at the stage of one iteration we are keeping the log of that particular node, how from where it gets results. Okay. So it gets an 1 divided by 4, which is an 0.25. We can say that. Sorry, 0.25. Right.
Sir, your screen is not visible, sir.
Not visible. So other students has visible. So it is visible to you guys. Manish, Kirti, my screen is visible to you guys, because yeah. So Jency, I think the issue from your side maybe. So up to now you have understood, right? Is there any issue? Please let me know. Jency, is it visible to you now?
Yes, sir, now it's visible, sir.
Okay. So have you understood how the weights are updated? A and B, C. No, no, no. Or should I repeat it?
Yes, sir, repeat once again, sir. I fifth question is not understand, sir.
Okay. Yeah, gets connected. So the question says that initially, uh, for each node we have an weights, which means we have a score, page rank score. Initially we have 1 divided by 4, which is an 0.25, right? 0.25 we have a score, and for each node, equally distributed node. So we have to find that what will be the page rank score of each node after the two iteration. So we can use any algorithm. We have two methods, equal distribution method and another one is an random walk method. So we have, for sake of simplicity, for the manual calculation, we have selected as an equally distribution method. Right? Equally distribution means what? Whatever neighboring nodes I have distributed whatever my page rank score equally in between the neighbors. And if it is undirected, it is distributed equally among the nodes, all the nodes, neighboring nodes. But if it is an directed network, in that case only the weights or the page rank score will be distributed among the outgoing edges only. It's not as an incoming edges. While solving this problem, you will get this many doubts clear while solving this problem. Okay, yeah. Let's carefully see this problem. So initially we have to select the random node from the network. Let's consider the random node is an A. We have selected. We have visited this node. Right. So initially we know that the node has an 0.25 weight. So B has an 0.25, C has an 0.25, D has an 0.25 weight. This is page rank score, we can say. And many time I am saying that weight, that terminology you can consider as an page rank score. Okay. So A has an page rank score which is an 0.25 and it has an two outgoing edges. So it is equally distributed in between the B and C. So after equally distribution, let's take as an how it equal distribution divided by 2, it gives an 125, that is 0.125. So it is, I'm considering, I'm keeping the log of each score, getting to the B, C, and every nodes. Okay, so B gets from the A is an 0.125 for the first iteration. That's why I have written 1 here. So for the first iteration, I'm getting C also getting as an 0.125. Right. So after visiting the A node, this is the state of the network. Okay. Then I have visited the B. Okay, any, but you have to visit the any random node as well. But I have going from chronology. Okay, so B have visited. So B have has initial weight is an 0.25. I'm not considering as an updated weights, that is an 0.125. Right, I'm considering the initial weights, that is an 0.025. So B has only outgoing edge and one only. That is the only neighboring node D, which is an outgoing node. So that is an 0.25 divided by 1, which is an all the weights. It's not distributed. 0.25 already uh, assigned to the B. Okay. So D has an outgoing edge, as an suppose I have visited. So C have not visited. B have visited. Let's visit the C. After visiting the C has an outgoing edges only one. So 0.25 divided by 1, which is an, it's, I'm right here, 0.25 divided by 1, because only outgoing one edge is going there. So for the B, so B has second score getting from the C, which is an 0.25. Right. Yeah. Then so where with, yeah, so after D, so we'll visit the D. After visiting D has an only outgoing edge as 1. It's going to the A, so it is directly assigned as in 0.25. Right. Yeah, so you can see all the nodes we have visited here. Right. So let's so this is the first iteration. The first iteration score we'll write here. The first iteration, the score of B or A. Let's A is an 0.25, but B has an 0.025 plus 125. What, how how much the score it is in? Maybe 0.375, right? And the C has an 1. So you can see I have highlighted the score. So might be you will get confused. I will erase some point. So only sorry, yeah. So this is the B. Then 0.25, no? Right. Sorry, 0.25, not that isn't 1.25. 0.125 because it is treated like points. Yeah, you can see here after the first iteration we are getting A node has an 0.025 weight page rank score, B get as an 0.035 score, C get as in 0.125. This is an updated score, page rank score, right? This is the initial one, but we are considered after the first iteration. So after the first iteration, what is the D score, page rank score, which is an 0.25. Okay, it is initial. Let's move to the uh, second iteration of the node. Okay, right. Mm. So is it right? Is there any issue or not? I think not. Let's move to the second iteration. 0.25, 0.375, 0.125, 1.0. Right. Okay, let's move to the second iteration. So I have visited again A. A has an two nodes. So again, there is a weight is an 0.25 here. So that is distributed here. I am taking the log as an 2 here. 0.125 it gets in the second iteration. Also in the second iteration, C got, list right here, C got as in second iteration as in 0.125. Okay, and so might be it's right and very far. The second iteration 0.125. Okay, because the same weight is there for A. And in B, if I visited the B, the B has an same weight, which is an, it's not distributed among the, because only the one neighbor is there, right? Which is, and second weight is in 0.375 decades, right? And after visiting the C, so which, maybe I will reduce the correct. I have visited this. This score is getting from this node, right? Then I have visited B. Then this score is updated, right? Then we have visited this C, right? The uh, C has an 0.125 weight, right? The 125 directly goes to this, this, right? 0.125. Is it correct? No? Previous, no, this one is in previous one, right? 0.25, right? Okay, it's fine. 0.25. It looks some confusing, actually. I am getting, yeah, I hope this is correct. Maybe let's see. Let me know if it is, I'm going wrong where. Right. Firstly, we have visited A. A has an 0.25 weight, so which is distributed among the B and C. We'll get as an 0.125 here and 0.125 here. Right. Then we have visited B. B has an 0.375 weight. The first from the first iteration, it goes to the D. Right here, because it is an same weight here. Right. Right. Then we have visited C. C has an 0.15 weight, right? The initial weight. Or, right. Hmm. 0.15, it goes to directly here to 0.125, right? Then, so we have visited A, B, C. Now we will visit to the D. Then D has an 0.375. So secondly, 0.375 goes to here, right? I hope you understood. Maybe one time I have stuck somewhere, but the all the calculation seems okay actually here. Okay, so let's write down here how which value we are getting. Firstly, the A has an after the second iteration we got as an A value which is an right. Uh, A value it is an oh second value will be goes to here, right? It's not an the first value I have written here, because this value will goes to here, right? The 0.25 and second value is 0.25. No, not as an second value, updated value, because I have a updated value I have written here. It's not like that. Okay, 0.25, right? B has an, you can see here, B is an 105 and 0.125, 0.125, which is an 0.25, right? So B is an 0.25, right? It is a 0.25, it's not an 0.5, right? Then C, you can see here 0.125, right? And D is n here 0.375. I think it's clear. So 0.25, how, what is this? 1.4, 0.25, 1.4, and 1.8, 3 by 8. Maybe it is correct. So I think it's cleared. Means if you have any confusion, I will thoroughly explain it again. It's not an directly I will calculate it. Okay. So any doubts? Maybe you have cleared it, or any doubts? Let me know. Yes, anyone? Anyone has means doubt or any confusion?
No, sir.
So here you can see the compare with the options here. 1 divided 5, 4, 1 divided 4, 3 by 8. Maybe this option is correct, fourth option. Right. So you have to log the whatever the scores you are getting at each vertex, and you have to make the addition here. You can see here we have done the addition here, then we have done the addition, and try means keep in mind that don't update this updated value. Means I have what I would did the mistake here, which has an updated value is in 2, that I have directly passed to the A. It's not like that. The previous value, what is the previous value of the D, right? That is in 0.25, that we need to pass to the A value, right? Yeah, I hope this concept is clear while solving the question. Okay. Let's move to another question. Pick out the invalid statement for wave graph. The wave graph, we have already discussed what is a wave graph represents. The wave graph, you can see each node represents as an web pages, and the edge represents an hyperlink in between the web pages. The node represents web pages, edge represents a hyperlink from one page to another way. It is a directed graph. It is a complete graph. So what do you think that which option is an invalid statement? It's very simple. Yeah. Is anyone?
I think second option, sir.
Uh, Jansi, why is that? Second option is the means in the wave graph, we are considering age as an hyperlink, right? Hyperlink means what? That from by using that hyperlink, we can go to that particular web page, which represents one age. Right? There is a node that represents a web page. Another node is an also web page. How it is connected? By using an hyperlink. This page has an one hyperlink, hypertext, right? The link is given in the page. So we are clicking on this page and then we are redirected to this another page, right? Which is connected by this hyperlink. Okay. So the in the web page, in the web graph, is represented a hyperlink, which can use for the jumping from one page to another page. So it is invalid. Let's think another options. Let's explore what could be the invalid statement. So consider in this graph, what could be the graph? What could be the invalid statement? This is also a real world problem. Real world network. It follows a scale free network. Scale free means that I have already explained that, which is an less degree node has a higher number of nodes. Higher degree nodes has a higher number means their number of nodes is very high, very low at that low degree nodes. Yeah.
Sir, option one.
No. See, I think you are not understood. See, we have a lot of web pages, right? So this is and let's see, this is and one social network web page, and another is an graph net web page. Means web page are there, right? Another sorry, another here is and let's take as in computer science, right? CS. So these are the web pages, right? Here, in the social network context, for solving the problem to search means so finding the important web pages, we design this problem into the network structure. So here, each web page represents as an one node, node from the graph, node of the graph. Means we have considered a graph. In that graph, node represents as an web page, and each web page connected by a hyperlink, which is an directed edge, right? In the CS web page, in computer science web page, there is a social network web page is also mentioned. There is a social network group, and that group web page is also mentioned in the CS, right? CS. So CS has a social network web pages represents an one graph, is graph theory web page. Right? This is how it represents. This is an hyperlink. Hyperlink means link, URL, right? Hyperlink each is able. So this represents a web graph, right? So considering this network, what could be the option is remaining? Already I have uh, given a one hint as well here. That is, in that hint there is a answer is also there. So what could be the answer here? Yes, anyone? Jancy, have you cleared it?
Yes, sir.
So
Third
then,
option is correct, sir.
sorry,
Third option.
it is a directed graph. See the question. They are saying which one is an invalid statement. It's not a correct statement. Pick out the invalid statement.
Yeah, okay, sir. I didn't saw question, sir.
Oh, so you are giving the correct answers. See here, the already mentioned in the web graph, this three is satisfied, right? No, no represents a web page. The age represents an hyperlink from one page to another. The third option is undirected graph. You can see is the direction is given to the link. Right? Three is incorrect related to the web graph. The fourth option says that it is an complete graph. Complete graph means what? Each node connected to every node. Every node. Let's take four nodes. So then the four nodes is connected to every each other node. Suppose node it is connected to all of his node. Then this is also connected to all this node. So in the real world problem, real world, this is a real world web page graph. In this, it is not possible. Every web page is not connected to all of the web pages, possible pages. Right? Means all of it's not only single. We are not uh, discussing about only single node, single web page. We are discussing about a lot of bunch of web pages, and those lot of bunch of web pages are connected to each other. All are connected to all of the their bunch of the node. It's not possible, right, in the real world problem. So this option is not correct. Complete. It's not a complete graph, right? This as considering this application, it's not complete graph, web page graph. So have you understood why it is not a complete graph? It's not possible in the real world problem, right? That every node is connected to every web page. Suppose there is an social network web page, and there is an another web page which is an um, which is an TV selling website, right? That is an web page. It's not connected to that web page, right? Because it's not context to, it's not related context to the TV selling or any television website. It's not related to social network, right? If there is a graph, definitely it may be connected, right? But there is an another domain web pages, and it's not possible, right? So considering this real world application, real world problem, it's not as a complete graph will be created of the web graph. Created means not make build from the real world web pages. Yeah, I hope this is great, clear. So second question, next question, which is also we have to solve that considering the following graph for the gold coins distribution, which is also equal distribution method. Each node in the graph, graph G, A, B, C, D, there four nodes are there, and has this is, let's see, this is an undirected graph. And the initial node, you can see initial weight of or page rank score of each node is an 20, 30, 45, 30, corresponding to the number of gold coins initially. So here the problem is stated like that: the each node, the four nodes are there in the graph, and the graph is an undirected. There is a no direction in the graph, right? And each node has an some initial gold coins. It's not as an we are calling it a page rank score, but in the context of the example that game has given, the each node has an some gold coins are there, right? So initially in the last previous example, we have seen every node has an equal score. Here you can see every node has a different score, different gold coins, and it is also indirected, undirected. What is the number of gold coins after one iteration? Last time we have done the two iteration. In this time we have to do one iteration. After the one iteration, what could be the possible gold coins at each node? Okay, let's start here. This is very simple. It's not very confusing. Already we have solved one example. I think first try to yourself try to solve this question. As I already solved the question, might be you have understood the how to solve or how to address this problem. Please take a time and try to solve this problem. It's very easy, and there is no difficult calculations are there also. Take a time and let me know what could be the answer. If it is correct, incorrect, it is also fine. Okay. So like these problems you will get in the final exam, right? So to while means with respect to the week wise, you have to solve this like these problems actually. So we will get a practice on that example, and you will get a familiar with that example. I think similar examples also you will get in this week assignment as well, right? So at that time also you will get help of these questions or this intuition what we are solving here. Anyone? It's very easy. It's not an difficult. Okay, I will go with. You can also solve with me along with me. Okay. If I'm going any wrong direction, please let me know. Okay. Yeah. So let's write the initial gold coins of each node with neighbor to that means along the side of that particular node. So the A has an 20. Oh, why it's 20. B has an 30. C has an 45. D has an 30. 30, right? So let's start from which node? So from previous, I already explained that we can start from any random node. So in previous example, we gone with the chronological order, but in this example, we'll take a random node. Taking random node, what could be the answer? Let's see. Okay, so the answer will same here. Suppose I have visited to A, C. C has an, this is an undirected graph. It's not we are looking only the outgoing edges. Every neighboring node is an outgoing edge. Let's so 45 divided by 3 because three neighbors are there. You can see here the 1, 2, 3. Three neighbors are there, right? So 45 divided by 3, its gate is an 15, right? This also gets an 15 because first iteration, and this also goes and gets an 15, right? So we have visited, done with this A. C, let's which node we can visit now. So let's visit the D, right? D has an two neighboring nodes, C and two neighboring nodes, sorry, C and B and C, right? So the B will get 15 from the D, C will get 15 from the D. Right, 30. 30 divided by 2. Simply we have done that. Right. So we have done with the D. Let's jump to the A. Randomly we are selecting the nodes. Unvisited nodes here. Right. So A has an two neighbors, C and B. Right. So it has an 20 gold coins. It is distributed equally among the C and B. The C will get. Taking a log here, keeping a log actually. One represents in first iteration. So that's why I'm writing 1, 1, 1. Right, 1, 20 weights are there. So the 10 here and 10 here. So A is done. Let's visit the B. So B has a three neighboring nodes, which is an D, A, and C, right? So 30 divided by 3, the 10, 10 each get. 1, 10, D get, C get 10, and B, A get as in 10. So all the nodes we have visited. Also cross check that each node has an gets weights from the equal number of his edges. So D has an two edges, so it has an two weights are getting, you can see 15 and 10, sorry, 15 and 10, right? So C has a three edges, so it gives three values, 15, 10, 10. B has an three edges, 15, 15, 10, 10. A has an two edges, 15, 10. Right. So now we have keep the log of the all the weights. Now we will do the final calculation. This is the first iteration we have done, and we want a first iteration result as well. Okay. So A has a total count is an 10 plus 15, which is an 25. Okay. B has a total count which is an 13, 15, 15, 30, 30 plus 40, 30 plus 10, 40. Right. So the final count of D, which is an 10 plus 15, which is 25. 40 C has a final count 10, 10 and 45, right? 30 plus 5. So here are the final counts 25, 45, 25, 40. Sorry, 40, right? 35. This is in 35, right? 35. See which option is correct. A has an 25, 25. Yes, Jansi.
Option 1 is correct, sir.
Yeah, option 1 is correct here. I hope you have understood the problem and process to solve the equal distribution method.
Yes, sir.
Yeah. Yeah, let's move to the another question. The other students is also understood, right? Anyone has any doubt? Manish, Lata. Okay, yeah. Let's move to the another question. Only the two, three questions are remaining. Okay. How is page rank vector typically computed in the page rank algorithm? Okay. So many times we have discussed the how the page rank works and how it is calculated, for which reason we have used a page rank, right? We have discussed in the while solving the questions, right? So considering that, which answer could be possible for this question? Anyone? Recall how which method we have seen the two methods in that how it works. Yes, if it is wrong answer is fine. Take a guess actually which one is correct. Yeah, the first option is that solving a system of linear equation, another using a recursive algorithm, right? Iteratively. So the option 4 is correct here. You can see here the first, the 2, 3 you are familiar means 1, 2, 3 are familiar with you. Means that we are solving a linear equation means there is an equation is forming, right? And that formed equation we are applied to that particular network and then we are solving it iteratively. Using a recursive algorithm, recursive means we are implementing again that mm, algorithm. So recall the random walk method, how the random walk method we are uh, um, implementing, or that one Dr. Sudarshan has already explained that one example, which is then you have a car and in you have a car and you are sitting in the car and you are roaming around a city and city has a no traffic and there is an uh, roads are there and you are going visiting every node every road, right, by driving the car actually and iteratively all the nodes you have visited many roads you have visited double or we can say repeatedly, but there is a possibility or there is an surety that after the implementing this random walk you will get visited all the nodes, right? So this is a recursive problem as well. It is a recursive iterative updating vector until iterative updating means we at each recursive point at each iteration we are updating the weights, right? The random walk how we are how the weights are updating, If I visited another node, whatever coins I have, I will give it to all the coins to the that visited node. That visited node has an he has already coins, right? If then the subsequent node he has visited, then all the coins he will gives to the his neighboring node. Likewise, the process goes on, right? So this is how the weights are updated, and at which point we have to stop, and which point the convergence state will comes. The convergence state means what? Firstly, convergence state means that we will get at that point of time as an optimal result. Optimal results means what is, okay, it's fine. Optimal results means what? The each node has get some weights, get some coins, gold coins. After further iteration, that coins number of coins is not changing. That is in final coins, means only decimal coins may be changed, but the overall coins are same after the some iterations. So that is a converged point, converging statement, that we can at that time we can stop the iterative process, right? So the three options are correct here, right, which says about the page rank. Right. So I hope you have understood the page rank that we have discussed. Let's move to the question 9, which is an in a graph, individuals with age representing friendship, uh, choose the correct option based on that. So let me explain the what the network represents. The node represents a user. That is, and let's assume that let's assume an Instagram application problem. So in the Instagram, there are multiple accounts, user accounts are there. Assume that or imagine that each Instagram account each is an one node. Sorry. Each Instagram account is an one node. And the relationship, right? There are multiple nodes are there. You can assume that or you can imagine that. Right? And each node is connected to the another user account by a friendship network. In the Instagram context, you can see that it isn't connected by following relationship, right? That user one account is following to the user two account. Likewise, so in the problem context, let's see that this is an undirected network, which is an user one user, another account is an one node is an another user connected by a friendship network. There is a no direction is going to this way or this way. They are following each other, right? Likewise, you can say that following each other means they are friend to each other. So let's move to this problem. So here is a network. Node represents a user. Age represents a friendship network. So considering this network, there are we have to see which option is correct. Statement one: take a random walk and drop one coin at each node while visiting. Individuals accumulating the most coins will be the most popular. Individuals means a user. The second option, second statement, given an equal number of coins to all individuals at the beginning, and then each individual has to distribute them equally to all of their friends at every snap. Every snap means every iteration. Likewise, after many iteration or many snaps, the individuals with the most coins will be the most popular. So, the considering this network and this statement, which statements are correct or which statements are wrong, incorrect? What do you think that? Yes. Anyone? It's very simple. The first statement says about the random walk. One coin, you will drop one coin at each node while visiting the another node. individuals accumulating the most, means users accumulating the most coins will be the most popular user. And another statement which is that given an equal number of coins, we have assigned the equal number of coins to all of the users at the beginning state or initial state, and then each individual has to distribute them equally to all of them their friends, okay, connected neighbors, at every snap. After many snaps, the individuals with the most coins will be the most popular. So which option is correct? The first option is correct or not? So you can see, you can correlate with this statement with the two methods we have seen. The first statement, it is related to random walk method, right? We're dropping your coins to the another user. The second statement is an equal distribution method, right? So each statement, each two of the methods gives us same, will solve the same problem, to find the important node or to find the popular node. So both the statements are correct actually. Right? So by using these two methods, we can find the popular node who has an highest number of points, because highest number of neighbors are there. Maybe he will get a higher number of points, and in that case, these two statements are correct. Right? I hope this you have understood. Is there any doubt in previous question?
No, sir.
Okay, which of the following are true for page rank and degree nodes? Yeah, take a time and let me know what could be the answer for this question. So the which of the first statement states that their correlation depends on the specific characteristics of the network. So this is a last question. Okay, after this we are turning off. The statement one, their correlation depends on the specific characteristics of the network, and they capture different aspects of the node importance. Yes, anyone? What could be the answer? So here the correlation depends on the specific characteristics, right? Because it depends. Suppose in the lecture series, in the lecture you have seen that the page rank score and the degree of the nodes is not correlating. Correlating means not getting a diagonal line, right? We are not linear line. We are getting it, right? That means it's not correlating, because correlating for a specific problem, because that is computed for the citation network, right? And for the citation network, it is, and vice versa, it shows the properties actually, means the web page has an highest citation, it means highest degree, which gives an lower page rank score. Likewise, vice versa, it's good. So for that particular application, it's not correlated, but it depends on the properties or the characteristics of the particular network or the problem, right? Likewise, it depends on the correlation of the page rank and the degree. If it is a highly, the problem is related to the degree, means who has unconnected highest number of important nodes, right? Highest number of important nodes, and he will get automatically the degree is high, and also the page rank score will be high in that case, in that particular application. Statement 2 states that they captures different aspects, right? It captures the different aspect. The page rank, it's not only consider the how many he has a neighboring nodes. It is also more than that actually. How much he it is and contextually importance. Means it is important related to your problem. Right? So both the options are correct here. Yeah, I hope all the questions or all means whatever the while solving the questions we have seen some concepts. Those concepts you have cleared or recalled from this question, and will definitely helpful for solving uh, this this week assignment questions. If you have doubts in between this week or means for these questions as well, let me know via mail. this is my mail ID. Okay, and the recording and the documentation of this say this week material, I will upload it on YouTube and the on the NPTEL as well. Okay, and that directory. Yeah. So anyone want to say something, or anyone has query, any issue, any difficulty? Okay. Okay. If not, we'll conclude this call. Okay. Yeah. Thank you. You can leave this meeting. Yeah.
Thank you, sir.
Yeah. Thank you.
Thank you, sir.
Yeah. Yeah. Thank you. Thank you.